Okay, hi everybody, and as we begin this video on this idea of what's called a linearization. A linearization is going to be a tangent line approximation for a function. So I want you to take a look at this particular graph of just everybody's favorite parabola, y is equal to x squared, and you notice that it's curved. I mean, that's one of the first things that you notice when you learn how to graph these things, is that it wasn't a straight line, it was indeed a curved pattern. And if we were to come up with a tangent line on this, well, we know a tangent line is straight. But how does that affect being able to find values of this function for, say, like, what's the square of 3.02, for example, or something like that, or even 1.8? Well, that may be hard to do without a calculator. But with a tangent line approximation, we can come up with what we think is a really good approximation. And why is that? Well, watch carefully as I continue to zoom in closer and closer, and zoom in closer and closer on an x value of, say, 1.8, or even let's go 1.2 because it's kind of in the bottom middle of the screen here. As I keep getting closer and closer to 1.2, you notice that even though we know this is a curve, it looks like this is straightening out. So the fact that this is straightening out is an indication that we've got a function that is what's called locally linear. So as we get closer and closer zoomed in, this function is going to straighten out, this curve is going to straighten out, and a tangent line approximation is going to be really faithful to an approximation for what the function is. So as we sort of kind of come back to the notes here, every differentiable curve is locally linear if you zoom in enough times. And that's kind of a good thing to know. So you can use a tangent line to come up with an approximation for a tricky function for values of x that are nearby. So you can find an approximation for the square root of 1.02 without having to reach for the calculator necessarily. Okay? And a fancy name for this equation of the tangent line is the linearization of f at a. And as you take a look at what we have written here in the box, y minus f of a is equal to f prime of a times x minus a. Well, this should look really familiar. This is point slope. This is point slope form that we have really spent a lot of time working with and getting to know over the course of this particular term so far. So if I wanted to get the linearization, then really all I needed to do is just move this coordinate over to the other side. That's going to give me what the linearization is. So if f is differentiable at some point a, then the equation of the tangent line, L of x, so we're going to write this as a function, is equal to f of a plus f prime of a times x minus a. And that is the linearization. And L of x is the standard linear approximation, and a is going to be called the center of approximation. So let's just kind of go ahead and see what we can come up with on a couple of examples here. So we're going to go and approximate the square root of 1.02, but we're going to use the linearization of f of x to find that, okay? So we're going to, at the end, use a calculator to sort of determine what the accuracy is on this, because, you know, sometimes when we make an approximation, we wind up trading accuracy for convenience, and we want to see how good this really is, okay? So if we're going to approximate what 1.02 is, square root of 1.02, what value of x do you need to use in this function to get square root of 1.02? Well, basically what we're finding is f of 0.02. Okay, so keep that in mind. That's what we're really trying to do here. So if I find this particular linearization, let's just kind of use, I think maybe we should use 1 as the center of approximation here, or 0 as the center of approximation to help ourselves out. Okay? Now, why 0? Well, because it's the square root of 1. We're going to use a linearization at the square root of 1 to help us out. So let's see what we can do with that. L of x is equal to f of a plus f prime of a times x minus a. Okay, well, if I let my a be 0 here, my center of approximation, well, then I can find these things pretty fast. F of 0 is going to be 1, of course, when we put that into our function right here. Let's find out what the f prime is. Well, the f prime of x is going to be 1 over 2 times the square root of x plus 1. Okay, and if I wanted to find what f prime of 0 was, I certainly could. F prime of 0 is going to wind up being 1/2. Okay, so with this information right here, the f of 0 and the f prime of 0, I can now start to find out what my linearization is when we're using 0 as kind of like our center of approximation. So it's going to be 1 plus 1/2 times the quantity x minus 0. So reducing this down, it's going to be 1 plus 1/2 x. And that's really not too tough to do. Okay, pretty straightforward. So this right here, friends, this is the linearization. Okay, so what I need to do next is I need to find the value of this at 0.02. So I'm finding L of 0.02. So that means I find 1 plus 1/2 times 0.02. Well, suddenly that's really easy to come up with. And here is our approximation. Okay, that's our approximation. So now what I'm going to do is I'm grabbing my calculator off camera here, and I'm going to find what the square root of 1.02 is. And if I do the square root of 1.02 in my calculator, and if I go to, let's go to several decimal places here, it's going to be 1.00995. Okay, now, as you're looking at this, if we were to round that to 2 decimal places, or even 3 decimal places, we'd end up with the same thing as we did right here. So I think our accuracy is pretty doggone good for this particular estimation. All right, let's take a look at another one here. At 2 point. Okay, we're going to find the linearization of L of x of f of x when f of x is equal to x third minus 2x plus 3, and a is 2. And then we're going to use that linearization to estimate f of 2.01. Okay, so we need to come up with what our linearization formula is. L of x is f of a plus f prime of a times x minus a. Okay, well, we need f of a first. And in this case, that's going to be f of 2. I think I can go ahead and erase that f of a, probably not needed for this particular problem. Let me get all those out of there. Good. Okay. And, well, let's see what f of 2 is. All right, 8 minus 4, I think it's going to be 7 is the way it looks. I think f of 2 is 7. So 2 cubed is 8, 8 minus 4 is 4, yeah, it's going to be 7. All right, and now I need to find f prime of 2. Well, that's going to be 3 times 2 squared minus 2. All right, that's going to be 10. All right, so what is my linearization? My linearization here, L of x, is going to be 7 plus 10 times x minus 2. Now, I could go ahead and simplify this into slope-intercept form because I think it's going to be pretty helpful for us to find out that information here. Actually, I'm not going to do it because you're going to see why in just a second. Now I'm going to use this linearization to estimate f of 2.01. Okay, so what I need to do in this case is, since my estimation is of 2.01, then what we're going to do is we're actually going to put in 2.01 into this. I know that was a little different than the last example, or so it seemed, but we were trying to need an x value. That's why it's a little bit different. So this is going to be 7 plus 10 times 0.01, or about 7.1 when it's all said and done. About 7.1. Okay, so once again, I think I want to get my calculator out here, and I want to find what this value is at 2.01. I really want to find out what f of 2.01 is as a number. So, and we are going to get that dealt with here appropriately. And when I do that, this is what I come up with to several places. I come up with 7.100601. So you can see that once again, our linearization is really, really good for something like this. Okay, last example, and this one is where we really make our money on linearization. We're going to find the linearization of cosine at pi over 2 and use it to approximate cosine of 1.6. Now, I should let you know that pi over 2 is about 1.57 in radians, and we're going to find out what the cosine of 1.6 radians is in just a little bit. Okay, so here's our L of x one more time. It's going to be f of a plus f prime of a times x minus a. All right, well, let's find out what f of a is. So our a is pi over 2, so pi over 2 is going to be the cosine of pi over 2, which is 0. Okay, that's going to be good news. All right, now let's find the derivative. And that's, of course, going to be negative sine of x. But I want to find out what f prime of pi over 2 is. Well, it works out to be negative 1. So this is going to be, get rid of that here. This is going to be 0 minus 1 times x minus pi over 2. Okay, so simplified, this is going to be negative x plus pi over 2. All right, so that's my linearization, but now what I need to do is I need to come up with what the estimate is for cosine of 1.6. Okay, so in order to do that, I'm going to find L of 1.6, okay, which is negative 1.6 plus pi over 2, and that should be negative 0.03 if I'm using this decimal approximation up here to help us out. And if I'm going to find the cosine of 1.6 radians in the calculator, you're going to love this. The cosine of 1.6 radians is about negative 0.02919995. So once again, we are seeing a very accurate look at an estimation for what a function is when we zoom in and get something locally linear. Okay, hope that helped the cause, and we'll see you soon.